They drilled for water. Instead, they hit temperatures that no geothermal system was designed to handle. This wasn't an accident. And it wasn't a disaster. It was a calculated engineering decision. In Iceland, geothermal energy powers everyday life. Hot water from deep underground heats homes, runs power plants, and does so with remarkable reliability. For decades, engineers had drilled into volcanic rock safely, extracting heat without crossing into danger. But by the early 2000s, a hard limit became impossible to ignore. Geothermal wells could only go so deep. Beyond a certain point, drilling deeper no longer delivered proportional gains. Temperatures rose, pressures increased, but energy output stopped justifying the cost. The system had reached its ceiling. So engineers asked a different question. What if the limit wasn't geological, but technological? What if drilling much deeper could unlock a state of water so hot and compressed that a single well could outperform several conventional ones combined? This idea became the Iceland Deep Drilling Project, or IDDP. The objective was simple on paper: efficiency. Drill deeper. Reach extreme geothermal fluids. Produce more energy with fewer wells. The location was Krafla, a high-temperature geothermal field shaped by volcanic forces and monitored for decades. It was considered one of the best-studied geothermal systems in the country. According to existing models, magma lay deeper than the planned target zone. The well was not designed to encounter molten rock. It was designed to approach it carefully and stop short. Steel casing rated for extreme heat was prepared. Specialized drilling equipment was deployed. The well began descending through layers of volcanic rock that Icelandic engineers had penetrated many times before. At the surface, operations appeared routine. But deep underground, something was changing faster than expected. As the drill pushed downward, temperature gradients steepened. Margins narrowed. Assumptions that had guided decades of geothermal drilling began to lose certainty. The project had not crossed a forbidden line. But it was moving closer to one than any geothermal well ever had. The deeper the well went, the more everything depended on precision. This was no longer routine geothermal drilling. Every additional meter increased temperature, pressure, and uncertainty. At shallow depths, geothermal systems behave predictably. Water circulates through fractured rock, heats up, rises, and can be captured safely. Engineers had decades of experience managing these conditions. But the Iceland Deep Drilling Project was moving beyond that comfort zone. The target lay several kilometers below the surface, far deeper than any geothermal production well in Iceland at the time. Here, water does not behave like water anymore. As depth increases, heat and pressure rise together. Past a critical threshold, liquid and vapor no longer exist as separate states. Instead, water enters an extreme condition, dense, highly energetic, and difficult to control. This was the prize. If the well reached these conditions, the energy potential would be unprecedented. But reaching it meant operating close to geological boundaries that were only partially understood. Steel casing had to withstand thermal expansion. Drilling fluids had to remain stable under extreme heat. Sensors were pushed toward the edge of their operating limits. With every section drilled, margins shrank. Models predicted rising temperatures. But the rate of increase began to outpace expectations. Rock formations changed. Thermal gradients steepened. Signals from deep in the well hinted that conditions were evolving faster than planned. Still, nothing had technically gone wrong. The well was intact. Pressure remained controllable. Surface operations continued without interruption. From above, the project still looked successful. But underground, the system was entering territory where human experience was thin. This was the point where the original objective quietly shifted. The project was no longer just about reaching a depth. It was about how close engineers could operate to an environment that had never been drilled into intentionally. They were approaching a zone where calculations mattered more than precedent. And precedent was running out. The first warning did not come as an alarm. There was no explosion, no sudden failure, no moment that forced an immediate shutdown. Instead, it appeared quietly in the data. As drilling continued, temperatures began to rise faster than predicted. Not outside safety limits. Not yet. But fast enough to draw attention. Thermal readings from deeper sections showed gradients steeper than the models had anticipated. Rock behavior changed subtly. Drilling resistance increased in ways that did not match previous geothermal wells. These were not errors. They were signals. Engineers compared measurements against forecasts. The well was still behaving within acceptable ranges, but no longer within comfortable ones. At depth, the distinction between hot rock and something else began to blur. Cuttings brought to the surface showed unusual characteristics. Textures suggested material that had experienced extreme heat. Not just fractured volcanic rock, but rock altered at temperatures higher than expected at that depth. Still, there was no confirmation of danger. The well remained stable. Pressure was manageable. Surface operations continued without interruption. From a project management perspective, this was not a failure condition. But from a geological one, it was a deviation. The subsurface environment was responding differently than anticipated. Models rely on averages. The Earth does not. Local conditions, pockets of heat, intrusions, variations in permeability, can change everything over a distance of just a few meters. At this point, engineers faced a familiar but uncomfortable decision. Slow down, or continue forward and collect more data. The objective had not changed. The well had not crossed any formal boundary. Yet the margin for error was shrinking. This was the first moment when the project entered a gray zone. Not because something had gone wrong, but because the assumptions guiding the drilling were no longer certain. The well was approaching something. They didn't yet know what it was. But for the first time, the data suggested that the system below was no longer simply geothermal. The confirmation came not as a theory, but as a physical event. At a depth of just over 2 kilometers, the drill encountered material it was never meant to touch. This was not hotter rock. It was magma. Rhyolitic magma, still molten, at temperatures approaching 900 degrees Celsius. For the first time, a geothermal well had not merely approached magma. It had drilled directly into it. The implications were immediate. Drilling could not continue as planned. The original target lay far deeper, but the well had reached a boundary that no engineering model had been designed to cross. Magma entered the borehole. Rock fragments recovered at the surface showed textures consistent with molten material that had cooled rapidly on contact with drilling fluids and steel. This was not an interpretation. It was evidence. From an engineering perspective, control was no longer guaranteed. Extreme heat threatened the integrity of casing and cement. Thermal expansion placed stress on steel designed for conditions that had already been exceeded. Sensors operated at the edge, or beyond, their rated limits. Yet there was no explosion. No eruption. No catastrophic failure. Instead, the system stabilized, just enough to reveal what had been reached. When the well was later tested, it produced superheated steam, exceeding 450 degrees Celsius at the surface. Pressures far surpassed those of conventional geothermal wells. The well had become something else. No longer a pathway to deep geothermal water, but a direct interface with the heat of the Earth itself. At this point, the original objective no longer applied. This was not an energy breakthrough. And it was no longer a drilling project. It was an encounter. The project had crossed from planned engineering into unplanned geology. And from here on, every decision would be about containment, not progress. When the well was opened for testing, the numbers alone were enough to change everything. Steam reached the surface at temperatures exceeding 450 degrees Celsius. This was not just unusually hot. It was beyond the operational range of conventional geothermal systems. At these temperatures, steel behaves differently, Materials expand unevenly. Cement can fracture. Seals degrade faster than they can be monitored. For personnel, proximity itself became a risk. Superheated steam at this level carries enough energy to cause severe injury within seconds. Standard safety protocols for geothermal operations no longer applied. Access zones had to be restricted. Monitoring became continuous. But the concern went beyond human safety. Releasing steam this hot into the environment alters pressure balances within the geothermal field. It can change fracture behavior underground, redirect fluid pathways, and destabilize zones that were previously predictable. This was no longer a closed system. The well had become a direct conduit between extreme subsurface heat and the surface environment. From an ecological standpoint, sustained operation at these conditions raised unanswered questions. Localized heating, chemical alterations in discharged fluids, impacts on nearby geothermal features that depended on delicate pressure and temperature equilibrium. None of these risks could be fully quantified in advance. What had been reached was not simply a hotter resource. It was a different class of environment altogether. Operating here would require new materials, new safety models, and a level of geological certainty that did not exist. At this point, continuing was no longer an engineering challenge. It was a responsibility question. So the objective was formally abandoned. Drilling operations were halted. The well was reinforced and reconfigured to contain the conditions already present. From then on, the focus shifted from extraction to monitoring. The project did not stop because it failed. It stopped because the consequences had outpaced control. This was the moment the line was drawn. Not by temperature, but by what humans could no longer safely manage. After the drilling stopped, the well did not disappear. It became data. For scientists and engineers, the encounter produced something that had never existed before. Direct measurements from a geothermal well that had intersected magma. This was no longer about energy production. It was about understanding conditions at the boundary between solid rock and molten earth. Researchers analyzed rock samples altered by extreme heat. They studied how magma interacted with steel, cement, and drilling fluids. They examined pressure behavior, heat transfer, and the stability of materials under conditions rarely observed outside laboratories. The results reshaped assumptions. It became clear that magma can exist closer to the surface, and in more complex geometries, than simplified models often suggest. It also revealed how narrow the margin is between high-performance geothermal systems and environments that overwhelm engineered control. But outside the scientific community, the story changed. Headlines reduced years of research into a single phrase. Scientists drill into magma. In some accounts, the well was described as a breakthrough. In others, as a near disaster. Details were simplified. Context was stripped away. The purpose of the project blurred. The distinction between controlled testing and uncontrolled risk faded. Public fascination grew, but understanding did not. The well became known not for what it taught, but for what it seemed to represent. A dramatic moment where humans went too far. What was lost in translation was restraint. The project did not end in chaos. It ended in measurement, monitoring, and deliberate limits. No eruption followed. No ecosystem collapsed. No catastrophe unfolded. Yet the story continued to spread, reshaped by repetition, shortened by retelling. This is often where science loses control of its own narrative. Not when experiments fail, but when complexity is replaced by spectacle. The aftermath of the drilling was not defined by what happened underground, but by how differently the same event was understood above ground. When the measurements stopped, understanding did not suddenly begin. It simply reached its limit. The well had delivered rare data. Temperatures, pressures, material responses. But only from a single point, in a single geological setting. Beyond that, the subsurface remained inferred. Scientists could confirm that magma existed closer to the surface than expected in this location. They could describe how engineered materials behaved under extreme heat. They could document what happens when geothermal systems approach magmatic environments. What they could not do was map what lay beyond the borehole. The size of the magma body, its shape, its connectivity to deeper systems, its long-term behavior. Those questions remain unresolved. Geological models can simulate possibilities, but they cannot observe directly. Every model depends on assumptions. Every assumption breaks down somewhere. The drilling provided a glimpse, not a full picture. It also raised a broader question. If this boundary exists here, how often does it exist elsewhere? And how close do human systems routinely operate to environments they only partially understand? The project demonstrated that technological progress does not advance in straight lines. It advances until it meets complexity. And then it pauses. Not because curiosity ends, but because certainty does. The Earth does not offer clean edges. Its systems overlap. Heat, pressure, and material states shift gradually. Until they don't. The well marked one of those transition zones. A place where solid ground gives way to molten uncertainty. For now, that boundary remains monitored, not crossed. Future projects may return with better tools, better materials, and better models. But even then, the same constraint will remain. Human knowledge expands through measurement, and it stops where measurement becomes impossible. This is where the story ends. Not with an answer, but with a limit. The data ends here. The exploration doesn't. Subscribe if you want to continue.